All right, hello, welcome to our final exam review for Math 2414. So I'm going to go ahead and start off with is I'm just going to go ahead and just cover all the new material that was not on exam 2. And then after that, I'll kind of just go through kind of like all the big highlights. And so I know this is a cumulative final, so I'll just kind of go through just some kind of big picture ideas on previous things. So with that being said, let us actually go ahead and get started. So our first new section that we have that was not covered on exam 2 is going to be section 11.4. And that one's going to be covering our comparison tests. So whenever we talk about comparison tests, we actually have two different tests that we're talking about. The first one we have is going to be our direct comparison test. And for our direct comparison test, the first stipulation we have is that where's my cursor at? I apologize in advance. My computer is acting kind of weird. I'm hoping I do not cut out this time, but we'll see. All right. So our first stipulation before we apply our direct comparison test is that both Series A and Series B are positive. So that's the first thing we have to just apply. If one of them is negative, then we cannot apply this test. So as long as that stipulation is cleared, there's two pieces to this. The first aspect states that if we have series b to the n, if we know that is convergent, and we know that a to the n is less than or equal to b to the n for all n, then our series for a to the n has to be convergent as well. The second piece of this is that if series B is divergent and a to the n is greater than or equal to b to the n for all n, then series A has to be divergent. And ultimately, this one is mainly just kind of comes down to common sense. So for example, if we have series A and we have series B, if B is bigger than A, and we know that B is like a finite number, then like A would have to be a finite number. But let's say we have A is bigger than B, then if we know B is infinite, then if A is bigger, then A also has to just be a bigger infinity. The main thing with this one is just make sure you don't get them like confused. So like for example, if we have, let's say we know that like a to the n is less than b to the n and b to the n is divergent, then you can't apply that because if b to the n is the bigger one, it doesn't matter if it's infinity. That doesn't tell us anything about a. We just know it's smaller, so it could be a smaller infinity or it could be a finite number. That just doesn't tell us anything. So just make sure you Just don't like kind of swap places on some of these. So with that being said, let's go ahead and do a quick example with our direct comparison test. So in this example, we have n squared plus 2 over n to the 4th plus 5. So the way we have this right here, we can't necessarily say for sure whether it's convergent or divergent, but what we can do is we can go ahead and try to maybe see if we can compare this with a p-series, because p-series are very, very easy to tell whether or not they're convergent or divergent. So we have two options. We can either take something off the numerator or take something off the denominator. If you can remove something from the denominator, but like if you have to only pick one, then I would try to maybe play with the denominator. Because the thing is, you can always split this up into multiple pieces. But like, so for example, we could take some, yeah, because depending on how we want to do our, it just kind of depends on how you want to do your comparison. So I would go ahead and compare this with n squared plus 2 over n to the 4th, because then we can break this up into two different fractions, whereas we couldn't if we did n squared over n to the 4th plus 5. So with that being said, let's go ahead and do our comparison. We know that this, so we can go ahead and break this piece down into n squared over n to the 4th plus 2 over n to the 4th. So first we have to make sure both of these are, if we want to prove that this is convergent, we have to make sure, of course, that both pieces converge. If one of these diverges, then the whole thing will diverge. So this n squared over n to the 4th, that can simplify down to 1 over n squared, which we know that through p-series, that is going to be convergent. If we look at our second piece, we get 2 over n to the 4th. Once again, we can use another p-series and know that that one is convergent as well. So we know that this whole thing is convergent and it's bigger, so therefore we know that our initial series has to converge as well. All right, so now let's go ahead and talk about our other test for this section, which is going to be our limit comparison test. So whenever we have a limit comparison test, we can go ahead and say that our main stipulation, again, we have to make sure that both A and B are positive. And our test states that if the limit as n approaches infinity of a to the n over b to the n is equal to some number c, and c has to be finite and c has to be greater than 0, then both a and b will diverge, or both will converge. And this one also kind of makes sense because if one of these went to, if let's say if A went to infinity, then our limit would be infinity. Whereas if B went to infinity but A was finite, then we'd be getting 0. So this is another one where it's just kind of common sense. For us to get a finite number for our limit, then they both either have to be infinity, and you just kind of think L'Hopital's rule will eventually take care of that, or you just get two finite numbers. So let's go ahead and do an example with this one as well. So for this one, we have our series n equals 0 to infinity, and then we have 1 over 3 to the n minus n. So if we just look at this right now, it's not really something we can easily really mess with. So usually whenever we do a comparison test, the best ones to use are usually going to be a p-series or a geometric. Mainly just because those are really easy to just look at them and say, I know that converges or I know that diverges. So because we have like 3 to the n, let's go ahead and actually try to do like a geometric to compare this with. So let's do 1 over 3 to the n, which we know will converge. And that can even be simplified down to 1 over 3 to the n. So now let's go ahead and play with this. So I think the easiest thing to do is to go ahead and flip this piece. Once again, mainly because we can break this down into multiple pieces. So we can go ahead and let this be our A, and this is going to be our B to the n. So we have A to the n over B to the n. So therefore, we're going to get limit as n approaches infinity of 1 over 3 to the n divided by 1 over 3 to the n minus n, which of course we can go ahead and flip that to make it easier to work with. To where we can get 3 to the n, 1 over 3 to the n times 3 to the n minus 1 over 1. We can go ahead and combine this to get limit as n approaches infinity of 3 to the n minus 1 over 3 to the n. We can go ahead and break this up. So we can get limit as n approaches infinity of 1, 3 to the n minus 3 over 3 to the n is going to be 1 minus 1 over 3 to the n, which will be 1 minus 0. Oh wait, I just realized did I miswrite this? Okay, I did miswrite this. N, that's an N, that's an N. So we know that's still going to be 1. However, our limit as n approaches infinity of n over 3 to the n, that's going to get us infinity over infinity. We can go ahead and do L'Hopital's rule to take care of that, so where we can get 1 over 3 to the n times natural log of 3 to get us 1 over infinity, which is 0, so we're still good over here. So therefore, our limit of the full thing is 1. So therefore, we get a finite number. And we know that a to the n is convergent. So therefore, b to the n, so therefore our original one has to be convergent as well. I'm gonna go ahead and like very quickly like talk about estimating sums. I don't think I saw any of like estimating sums with limit comparison or integral on your review, but just in case, I won't do an example, but just do a really quick review of the concepts. So for that, give me just a second to pull up my notes for this. So just a really quick, just a really quick recap of estimating sums. Like if you get a sums question with the series, it'll likely, I would imagine on the final, I don't know 100% for sure, you're almost guaranteed to get a geometric sum. They may give you a telescoping. And I know on your review, I know they did have some involving like Maclaurin and Taylor, like a Maclaurin and Taylor series, but we'll get to that when we get there. And that one would be more alternating series, so I don't think you'll get a ton of integral slash limit comparison, but just in case. Just the main thing we know is that, let's say we can define sequence A, and we can say that the remainder of sequence A is the sum minus the partial sum. And we can define that as just saying a to the n plus 1 plus a n plus 2 plus a n plus 3, and so on and so forth. And let's say we have sequence B, and we can say that the remainder for sequence B, which we'll call T, is that sum minus its partial sum. So we'll say b n plus 1 plus b n plus 2 plus b n plus 3. So where the limit comparison part comes in is that we can say if a is less than b, then r has to be less than t. And then essentially there's a couple ways where they could give you this problem. Essentially they could either give you a p-series or a geometric. If B is a p-series, then you'll go ahead and use like the integration form for the sum and like for the remainder, and say that your integral from n plus 1 of f of x dx is less than or equal to t, which is less than or equal to your integral from n to f of x. And going off of that, we can also say if we add t to the n on both, if we add our partial sum on both sides, then we can go ahead and compare directly with our actual sum rather than our partial sum. Rather than our remainders, then we can also look at our like whole sum as well, rather than just our remainder. And if B is geometric, then you can just use kind of use your geometric sum formula. And then just know that like your remainder is going to be smaller. And then just compare like your remainders, compare your sums, all of that jazz. But yeah, I don't imagine you'll get any questions on that, if any. So the ones that they usually would ask more about would be alternating. Like I said, the ones that they ask more about are alternating, just plain geometric sum, like no comparison or anything, and maybe telescoping. All right, so let's go ahead and move on to alternating series. All right, so alternating series, those are pretty much essentially, I mean, it's what it sounds like. Alternating series, they're going to bounce back and forth between positive and negative terms. And essentially, they're going to look something like this, to where you can have your alternating series A will be equal to either -1 to the n times b to times some other b to the n, or you'll get -1 to the n minus 1, or maybe n plus 1 times b to the n. So whenever we test for convergence and divergence with alternating series, then we have to go ahead, then we have two stipulations for that. If our limit as n approaches infinity, b to the n, so pretty much the rest of the series that's not the alternating part, is equal to 0, and the terms of b to the n, or the sequence, are decreasing, then your full series a to the n will be convergent as well. We'll go ahead and converge. If one of these stipulations is not met, then it'll diverge. So just a quick example for this one. We have cosine of pi times n over the square root of n. So this one's kind of different because we don't have an explicit -1 to the n. But we do have a pi n, but if we have a cosine of pi n, then we know that can bounce back, that's going to bounce back and forth between -1 and 1, right? So therefore, we can rewrite this as an alternating series. We're starting off with 2n, so cosine of 2 pi is positive, so we're just going to go ahead and do an n plus 1 right here just to keep it, just if we're going to be nitpicky, go ahead and apply that. But the main part we care about, of course, is going to be the rest of this function, so the 1 over square root of n. So we have 1 over square root of n. So the first thing we can do is we need to take our limit. So we're going to get, as n approaches infinity, so 1 over infinity, which is 0. So therefore, our first criteria has been met. And now we have to just make sure that our terms are decreasing. And if we think about it, each term, because our numerator stays the same, but our denominator gets bigger, the terms will decrease. And like you can even just look and just say 1 over square root of 2 is greater than 1 over square root of 3, which is greater than 1 over square root of 4. And so therefore, our second criteria has been met. Therefore, this series will go ahead and converge. All right, so just to go ahead and touch on estimating sums. For alternating series. So we actually have a theorem for this. So the theorem states that if our sum is equal to the series, is equal to an alternating series, so -1 to the n minus 1 times b to the n, where b to the n is otherwise positive. Yeah, where b to the n is positive, and the sum yes, and S is the sum of a convergent alternating series, then the remainder of our alternating series, or the absolute value of our remainder, is going to be equal to the absolute value of our sum minus our partial sum, and that's going to be less than or equal to b to the n plus 1. So I don't actually have an example for this one written down, but usually the way you'll see these is they'll ask you for like an error approximation. So what they'll go ahead and do is they'll say like approximate this to some error, or like approximate this sum to X amount of decimal places, and then you'll go ahead and use that as like your R to the N and use that to go ahead and like compare. And usually, eventually, you may need to go ahead and solve for N. So let's go ahead and move on to section 11.6. So therefore, this so section 11.6 is going to be covering ratio and root tests. So before we cover that, we need to go ahead and just do a quick review. We've introduced new terminology in this section, so absolutes versus conditional convergence. So absolute convergence means, so whenever we say like a series A is absolutely convergent, that series A is absolutely convergent if the absolute value of that series is also convergent. Whereas conditional convergence states that A to the n is convergent, but our absolute value is divergent. Or otherwise, it just essentially means we don't quite meet, your initial series is convergent, but you don't meet all the criteria for absolute convergence. So usually of course, the main place you'll see this, we're looking at absolute value, is usually going to be with an alternating series. So now that that's out of the way, let's go ahead and talk about our ratio test. So our ratio test states that it has three pieces to it. It says that if the limit as n approaches infinity of the absolute value of a the n plus 1 over a sub n is less than 1, then your series A, and then your series A is absolutely convergent. The second piece of this states that if the limit as n approaches infinity of a sub n plus 1 over a sub n is greater than 1, then your series will diverge. And the last piece states that if our, limit of our ratio is equal to 1, then our test will fail, and you're going to have to go ahead and try something else to determine whether or not your series is convergent or divergent. So let's go ahead and do an example with this one. So in this example, we have our limit as n goes from 1 to infinity of 9 to the n over negative 2 to the n plus 1 times n. All right, so what we can do, first we can go ahead and plug in our n plus 1. So every place we have an n, we'll replace that with an n plus 1. So we can get 9 to the n plus 1 over negative 2 to the n plus 2, I mean. So n plus 1 plus 1, so n plus 2 times n plus 1. And you're going to either divide or just multiply with the reciprocal of our initial sequence. So 2 to the n plus 1 times n over 9 to the n. All right, so we can go ahead from here and start canceling things out. We can go ahead and cancel out this 9 to the n and then the 9 to the n plus 1 to get us just plain 9. Similarly, we can go ahead and cancel out the 2 to the n plus 1 and the negative 2 to the n plus 2 to get us negative 2 right here. So from here, we can go ahead. Let's go and rewrite this to make it a little cleaner, and we can go ahead and take our limit. So we have our limit as n approaches infinity of, we have 9n over negative 2. We can go and distribute that negative 2 to get us negative 2n minus 2. So looking at this, we're going to go ahead and get infinity over infinity. We can go ahead and do L'Hopital's to get us limit as n approaches infinity of 9 over negative 2. So 9 over 2, which we know is greater than 1, so therefore this will go ahead and diverge. So the last thing we have in this section is going to be our root test. All right, so we have a root test, and it states that so it's pretty similar to our ratio test. There's just a, so once again, 3 conditions. First one, if the limit as n approaches infinity of the nth roots of the absolute value of a sub n is less than 1, then your series is absolutely convergent. Second stipulation states that if the limit as n approaches infinity of your nth roots of the absolute value of a sub n is greater than 1, your series is divergent. And the last one states that if the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to 1, test fails, try something else. All right, so I'm going to go ahead and do another quick example for this one. So this example, we have 5n minus 3n cubed over 7n cubed plus 2 all to the n. So this one we see that obvious exponent n, so that's a pretty good sign to go ahead and use our root test. So we can go ahead and take our limit as n approaches infinity of the nth roots of the absolute value of 5n minus 3n cubed over 7n cubed plus 2 to the n. Those n's will cancel out. So where we now have the limit as n approaches infinity of the absolute value of 5n minus 3n cubed over 7n cubed plus 2. The easiest thing for this one would probably just be divide everything by n cubed, just to make that easier. That way we won't have to do L'Hopital's rule a ton, so therefore we can get our limit as n approaches infinity of 5 over n squared minus 3 over 7 plus 2 over n cubed. And then therefore we'll get the absolute value of 0 minus 3 over 7 plus 0. That will get us 3/7, which we know is less than 1. So therefore we can say that this series is absolutely convergent. All right, so then next one I want to just quickly touch over is just quick strategies for series. So overall, whenever you're trying to go ahead and determine convergence and divergence, the main thing you want to look for is going to be the form of your series itself, rather than just being like, oh, let me just because that just makes it easier to narrow down which tests you want to apply. So just some kind of quick tips for format. If you have anything with some sort of like 1 over n p into the p, so just n to something, that's an automatic p-series. And of course, if p is greater than 1, it is convergent. The next thing to look for is your geometric series, so which we know is going to be some AR to the n minus 1 or AR to the n. So of course, like we said, that's a geometric series, and you know that one's going to be convergent if the absolute value of r is less than 1. And for that one, they could potentially ask you about your sum. And your sum for that one will be, let me pull up my notes. Your sum for that one will be a over 1 minus r. The next thing it says, if your series is similar but not exactly to a p-series or geometric, go ahead and use your comparison test, because that'll just usually the easiest thing to go ahead. And those are like I said, p-series and geometric, those are pretty obvious whether or not they converge or diverge. They're very easy to compare with. So if you can use those, use those. Our next tip is that don't forget you have your trusty test for divergence. So remember, we have if our limit as n approaches infinity of your sequence does not equal 0, that's full stop, that will go ahead and diverge. Five, we have 5 is pretty easy, alternating series. We'll have either a -1 to the n or a -1 to the n plus 1, plus or minus 1. Those are pretty obvious those are usually obvious to spot. You may have some like that trig one we did in our example where you may have to play with it a little bit, but usually they're pretty obvious to spot. If you have any factorials, or if you have some sort of something to the nth power, or some sort of product, like something multiplied together, I would go ahead and use ratio tests, because those make it really easy to go ahead and cancel out some factorials, some exponents, and usually products, you can usually end up taking care of those whenever you find your limit. And then if you have some sort of like sequence where it's essentially like a sequence raised to the power n, that's an obvious sign for root test. And lastly, if you can easily turn this into like an easy function to integrate, then just go ahead and do your integral test. All right, we're at a good spot right now. Does anyone have any questions before we move on to power series? Okay, that's a good question. So this will be uploaded. Just look up UTD peer tutoring to look at this review. Like we have a YouTube channel. Go to UTD peer tutoring. If you go to playlist, it'll be located in the spring 2021 exam review. Just go in there. It should be uploaded either later this evening or tomorrow evening at the latest. All right, so now let's go ahead and move on to our power series. Wait, let me check the chat real quick. And on some of these, if like there's a topic I didn't really get to cover a ton, you can always check the other weekly reviews on there, check the other exam reviews. So especially since we're kind of a little behind on time, I may not get to cover as much of like the older materials I would like, but we'll get what we can done tonight. All right, so power series. So our power series will have the general format of some sort of n goes from 0 to infinity of some c to the n, which is what we call a coefficient. And that can just be, it can be a constant number, it can involve some other part of like a series, like anything involving n. It's just something out in front. The thing that defines it as a power series is you'll have this x minus a to the n, or you may just have x to the n. So your power series, they don't necessarily have to have a coefficient. They don't necessarily have to have like a minus a, but they're always going to have like some sort of x to the n. That's how they're going to be defined as a power series. So whenever we talk about convergence with power series, there's actually 3 different ways this could work. So your power series could be convergent only at x equals a, so like only at like this little mid piece. It could be convergent for all values of a, or I mean for all values of x. Or you could have something that's in between. What could happen is you can go ahead. So essentially what you'll have is there is a positive r such that the series converges if the absolute value of x minus a is less than r and diverges if the absolute value of x minus a is greater than r. So whenever we talk about power series, we can think of it as like it's a series centered around some number a. And essentially what this is saying is we can go, it may converge like up to some r value away from a. Once you get past that distance of r, then it'll diverge. And in here, R is what we call the radius of convergence, because like that's essentially the radius away from that midpoint that you can go for it to still converge. And from here we can get what is called the interval of convergence. And that is essentially just saying like all x values. That's essentially just listing all x values that converge. So I'm going to go ahead and do an example with this one. So what we're going to do is we're going to have our series of 2 to the n over n times 4x minus 8 to the n. So typically whenever we have something like this, so essentially we want to figure out like what x values will this converge. So typically the easiest way to do this is to compare this with either your ratio and or your root test, because that gives you something that's very, very easy to compare and say like, okay, I know it diverges, I know it converges up to this point, and then after that point it will not it will diverge. So what we can do is we can actually go ahead and apply this to, let's go ahead and use our ratio test. That like 1 over n can kind of, that may mess with us. So let's go and do a ratio test rather than our root test. But I mean, you can try this at home with a root test if you want to. So whenever we do our ratio test, we can go ahead and do our n plus 1. So we have 2 to the n plus 1 over n plus 1 times 4x minus 8 to the n plus 1 times our reciprocal of the original. So we can do n over 2 to the n times 4x minus 8 to the n. We can go ahead and get ready to take our limit. Go ahead and set up, and we can go ahead and first let's go ahead and cancel some stuff out. We know we can cancel out this 4x minus 8 to the n with all of these except for 1. We can get rid of that exponent. We can do the same thing with this 2 to the n, and just be left with 2. So therefore we have our limit as n approaches infinity of 4x minus 8 times n over n plus 1. And we know for this to converge, this has to be less than 1 for this to converge. So typically what I find easiest to do is I actually like to just go ahead and like pull out that 4x minus 8 and just pull that out in front. Because that's not going to affect our limit because of that x. All we care about is the stuff with an n. So we have our limit as n approaches infinity of n over n plus 1. And we know that all of that product has to be less than 1. So we know the limit of n over n plus 1 will go ahead and get us, 1, because just looking at it, you know, same coefficients, same exponents, it's just going to go to 1. So therefore we can say that our absolute value of 4x minus 8 is less than 1. But we can also take care of that absolute value by going ahead and we can go ahead and get rid of our absolute value by saying that -1 is less than or equal to, or for now, let's just say less than 4x minus 8, which is less than 1. So now we can go ahead and check our x values to see what our interval is. So we can go ahead and get 4x minus 8 is equal to 1. So we can get 4x is equal to, so we can get 4x is equal to 9 over 4. Wait, actually, give me a second. I think I forgot a 2. My bad. I forgot that 2 up there. I was thinking this doesn't match. I was like, this doesn't match my notes. So that limit will go to 2. There we go. So now we have 4x minus 8 times 2 is less than 1. We can go ahead and divide by 2. And get 1/2. And we can go ahead, whenever we're at just the absolute value by itself, that point is going to be your radius of convergence. But now if they're asking for our interval as well, we now have to go ahead and check our x values to see where those apply to. So we can go ahead and get rid of our absolute value by saying -1/2 is less than 4x minus 8, which is less than 1/2. We can go ahead and solve both sides of the inequality. So we can get 4x minus 8 is less than 1/2. 4x is less than 17 over 2. And then we can get x is less than 17 over 8. And then over here we can get -1/2 is less than or equal to 4x minus 8. Then we can get 15/2 is less than 4x. And then 15/8 is less than x. So we're almost done. We kind of know our, so the last thing we have to do is check our endpoints. So what we're going to do is we're going to plug our endpoints back into our original power series and see if it still converges. So our original power series was I believe we did n equals, n equals 0. To infinity of 2 to the n over n times 4x minus 8 to the n. So we're going to plug in those values for x. So we can say we have 2 to the n over n times 4 times 15/8 minus 8 to the n. 4 times 15/8, this is going to go ahead and cancel down to 15/2 to the n over n. So we can get 15/2 minus 8, which is going to be -1/2 over here, let's go and plug in our 17 over 8. We can get 2 to the n over n times 4 times 17 over 8 minus 8 to the n. That will cancel down to 17 halves. 17 halves minus 8 will be 1 half. All right, so now what we can do is we can go ahead and check both of these for convergence. This one right here, we can go ahead and combine those n's, that 2 to the n and that negative 1 half to get us negative 1 to the n over n. And then over here, what we can do is we can go ahead and once again combine those to get us 1 to the n, which is 1 over n. So right here, this one we can use our alternating series test. We can see that our limit will go to our limit of 1 over n will go to 0, and it'll decrease. So we can say that this one is convergent. But then we have this one. We have a 1 over n, and we know from our p series that it has to be greater than 1 for it to go ahead and converge. So this one will diverge. So therefore, our interval of convergence would be bracket 15 over 8 to 17 over 8 with a parentheses. All right, so now we're going to go ahead and move on to representations of power series. Yeah, functions as power series. So whenever we have, so what we can say, so if we have the function f of x is equal to 1 over 1 minus x, that is actually equal to the power series from n from 0 to infinity of x to the n. But what we can do is we can also kind of treat this almost kind of like a u sub or something along those lines. If we had, let's say, f of x squared is equal to 1 over 1 minus x squared, that would be equal to just plugging in x squared to the n. So essentially what we can do, if we can get this format to where we can get 1 over 1 minus some x, or you can call it maybe some u, something along those lines, you can plug that part straight into a power series. And that will be what is called a power series representation of a function. So let's go ahead and do let's go ahead and do an example of how, like, to kind of show how this one works. Like, you're usually going to have to manipulate the function a decent amount to go ahead and actually get you into a format where you can do a power series, but usually it's not that bad. Like, I doubt on the exam they'll give you something that's absolutely disgusting to manipulate. So for this one, we want to turn f of x is equal to x over 5 minus x into a power series. So we want to ultimately get into the form of like 1 over 1 minus x, or like 1 over 1 minus u, something along those lines. So what we can do first is we can go ahead and pull out an x and just factor out the x and say that we have x times 1 over 5 minus x. So now we're a little closer. The thing is, we still need to have that 1 minus something in the denominator. So what we can do is we can actually go ahead and factor out of 5 from our denominator and get x times 1 over 5 times 1 minus x. Or if we want to clean that up, we can get x over 5 is equal to 1 over 1 minus, wait, that's an x over 5. There we go. 1 minus x over 5. Now we're in the form that matches like this up here, this 1 over 1 minus u. So now what we can do is we can plug that x over 5 into our power series. So our power series will be from 0 to infinity, and it's whatever this is to the n. So we can do x over 5 to the n. Oh, wait, do we have a question in here? X over 5. Like in this example, it's x over 5. So yeah, what we did was we went ahead and we pulled out, oh, the equal sign. Which one? Okay, yeah, after you pull out the 1 over 5. Okay, yeah. So yeah, what we do is, so yeah, we have x, and we factored out a 5 from just the denominator. But then whenever we go ahead, we can actually pull that out in front and kind of rewrite that as like, because this could be rewritten as like 1/5 times 1 over x minus 5. So I just did okay, wait, what happened to my connection? All right, let's see, am I good? Okay, yeah, did that answer your question though about, yeah, I think I miswrote that. There we go. Yeah, thank you for catching that. So yeah, we have that x. So yeah, we went ahead, we plugged that x over 5 into our power series. Yeah, we just plugged that straight in here. But we also have to remember we had this x over 5 multiplied right here. So we're going to go ahead and have this out in front of our power series. But really, to make this cleaner, what we really want to do is put this back inside of our series. So what we can do is we can go ahead and rewrite this as x over 5 times x over 5 to the n. But since those are both x over 5, we can actually go ahead and move this in here and then change the exponent to n plus 1. So where we have x over 5 to the n plus 1. Now, this one was a fairly simple example, but just a thing just to kind of be aware of is if you have something that's a little bit more complex, I would actually go ahead and separate that x over 5 into something like this, to where you have x to the n plus 1 over 5 to the n plus 1. And usually I'd actually separate it probably at this step right here, to where you'd have like x over 5 times x to the n over 5 to the n, just to kind of keep track of like where all of your x's are coming from, where all of like your coefficients are coming from. Like this one is a pretty simple example. This one is very straightforward, but not all of them will be this simple or straightforward. I think I had a couple in my weekly review where like you kind of had to really, really pay attention to where all of your x's were coming from, and you really had to pay attention to your exponents. So there's actually another aspect of power series that we need to go ahead and take into account. So that format is pretty simple. It's really not that bad to work with if you have like one term over, it's like if you just have a very simple numerator, denominator, something like that, where you have like some a over some like c minus bx, or something along those lines, to where you can really easily move it to where you can get your 1 over 1 minus x format. But the thing is, not all series are going to lend themselves to, but not all functions will lend themselves to that. So that is actually where differentiation and integration come in with power series. So essentially what this states is that if we have the power series of our coefficient times x minus a to the n has a radius of convergence greater than 0, then the function f is defined by f of x is equal to c sub 0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on and so forth. So eventually that is essentially just our initial power series. Well, that function then from there we can say that f is differentiable on the interval a minus r to a plus r. And let me go ahead and scroll down. F prime of x is equal to, I'm actually let me go ahead and scroll back up so you can, okay, that's not going to be able to put both on there. Okay, I need my laptop to stop being weird. Come on, laptop, please. Back to normal for the next 30 minutes. There we go. C1 plus 2C2 x minus a plus 3C3 x minus a squared. So this is essentially where we took the derivative of each individual term, and we can say that that is equal to the power series n times c sub n times x minus a to the n minus 1. So essentially we're able just to derive our series with respect to x. And we can also go the other way. We can go ahead and actually integrate. So we can say the integral of f of x dx is equal to c plus c naught x minus a plus c1 times x minus a squared over 2 plus c2 x minus a cubed over 3, and so on and so forth. And we can say that that is equal to our power series Cn times x minus a to the n plus 1 over n plus 1, and then you're also going to have a little plus c out here. That's like when you integrate normally. So usually what we do, so the reason why we talk about this is so we can actually manipulate some other functions to turn those into power series. So usually sometimes what we can do is we can integrate a function and then turn that into a power series, but the thing is we've integrated that function. So to get back to the original, we'd have to derive our power series. Or let's say you derive a series, so you derive something to get to a power series. Well, that power series is of the derivative of your initial function. So therefore, you'd have to integrate to get back to the original. So just as a quick example, kind of showing this, we can say that we have f of x is equal, so let's say we have our function f of x is equal to 1 minus x squared. We're not, because of this, we're not in a format to where we can easily just go, okay, that's 1 minus x, because that x, you know, that squared down there is going to mess up, is kind of messing stuff up. But what we could do is we can integrate this function. We could integrate both sides to get us f of x is equal to, we get 1 minus x, and we have a negative 1 up here. So we're not quite in the same format, but we can actually play with that negative 1. So we can actually go ahead and move the negative down to the denominator to get us 1 over negative 1 plus x, which is 1 over, wait, let me double check this real quick. Okay, yeah, I think there is, yeah. So what we can do, yeah, actually, yeah, don't worry about, yeah, don't worry about that. We're good from right here. So therefore, we can just pull out that -1 out in front, so we can get -1 times 1 over 1 minus x. And then from there, we can go ahead. This is just our straight power series to where we can get a negative n goes from 0 to infinity of x to the n. But we have to remember we integrated to get to this point. So therefore, we're going to have to derive to get back to our original. So like this is like our big F. So now we're going to have to go ahead and take our derivative. So therefore, we can get f of x is equal to negative series from n goes from 0 to infinity, n times x to the n minus 1. All right, so now we're going to go ahead and try to touch on Taylor and Maclaurin real quick. Hopefully we have some time at the end where I can maybe go over like some other concepts y'all may have questions with. All right, so the main thing you need to know for Taylor and Maclaurin series is that our Taylor series, so essentially what we know is that, so pretty much this is based off of power series, but essentially like a Taylor series is kind of like a very specific power series. So your Taylor series is essentially where you can have your function be equal to a series such that n goes from 0 to infinity of f to some derivative, like that's like f to that n, that means like that's like the nth derivative of some number a over n factorial times x minus a to the n. And like a is like your midpoint, or like center is going to be like your center. And just to kind of show like how this would look like if you expanded this out, so like the first few terms would be like f of a plus f prime of a over 1 factorial plus f double prime of a over 2 factorial plus f triple prime. Oh wait, I forgot this is times x minus a. This is times x minus a squared. Then f triple prime of a over 3 factorial times x minus a cubed. And so on and so forth. And then from there, we can actually get even more specific. So Maclaurin series are just very specific, or more specific Taylor series. So Maclaurin series are essentially Taylor series, but they're centered at 0. And their format will be f of x. Your function will be equal to a power series to where you have the nth derivative of 0 times over n factorial times x to the n. And if you expanded that out, you would just get f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so on and so forth. So whenever it comes to dealing with Taylor and Mclaren series, they are, I'm not gonna lie, they are kind of tricky to deal with. There's a lot of pieces to it. You kind of have to be good at deciphering patterns, but still we can go ahead and work on trying to do this. So let's actually do an example. Let's first do a Maclaurin, then I'll look at the time and we may do a Taylor. So for example, we want to go ahead and find Mclaren series for f of x is equal to e to the negative x. So typically the way that I would usually start by doing for both Taylor and Maclaurin series, I'd go ahead and split this up into columns. Your first column is you're going to look at all of your derivatives of your function. So you're going to start off with your f of x, f prime, f double prime. I'd usually go up until about your third derivative. I'd usually go start from there, and then if you can find your pattern, great. If you don't quite have a pattern yet, then you can always add on. So yeah, so essentially the main thing is we're trying to go ahead and find like a formula for like our nth derivatives. So we have our f of x is e to the negative x. If we take that, take that derivative, negative e to the negative x, take that derivative back to e to the negative x, third derivative e to the negative x. So then now what we want to do is we want to go ahead and look at that specific point. So if we're at Maclaurin, we know that we're centered at a equals 0. So f of 0, f prime of 0, f double prime of 0, f triple prime of 0. So we have e to the negative 0. So we're just going to keep, is going to be 1. Negative 1 times 1 is negative 1, 1, negative 1. And we can see how we're just going to kind of keep following this pattern pretty much forever. All right, so whenever we do this, now we can go ahead and let's try to find a pattern for both our f of x and then our f of 0 columns. So for f of x, we can see how we're just going to kind of oscillating back and forth between positive and negative e to the x. So we can say that if we have the nth derivative of f of x, that will always be equal to, since we're going back and forth between positive and negative, that's a clear indicator that we're going to have a negative 1 to something. And if we start off, we know we're starting off positive when n is 0. So therefore, we can just say n. Because negative 1 to the 0 would be 1, positive 1, and that matches, times e to the negative x, since that's going to be the other piece that we're going to always keep. And then we also have, so now we can find one that's a bit more specific. So we have our nth derivative of 0. We can see how we're just going back and forth between positive and negative 1. So therefore, we can just say that is negative 1 to the n. So now we've actually found, so now that we've found these pieces down here, we can actually go ahead and get ready to apply this to our actual formula. So if we scroll back up, we have, where'd it go? We have this formula right up here. So we have actually, now that we have found our nth derivative of 0, we can actually go ahead and plug that straight into that formula and say that f of x is equal, yeah, so we have f n of 0 over n factorial x to the n. If we scroll back down, not that far. We can see how we have our fn of 0 right here, fn of 0 right here. So now we can just plug that straight in to our formula, so where we can get f of x is equal to negative 1 to the n over n factorial times x to the n. And that will be our final answer. So it is 6:30. We can be here for another 15 to 30 minutes. Would y'all prefer me to do a Taylor series example, or would y'all prefer for me to do other just general review on like integration, polar, parametric? Which would y'all prefer me to do? Because that, all right, I see, it looks like more people, yeah. If we have time, we can go ahead and we can go back and do another Taylor, do that Taylor series example. But yeah, we can go ahead, since more people seem to want to do some general review, we can go ahead and do that. All right, so let's go ahead and think about some other stuff. Let me actually go and pull up my previous exam review notes. All right, so just some kind of general concepts. Yeah, we're just going to go ahead and try to speed around a little bit through a few general concepts. So let's go ahead and think back to, let's go ahead and just go way back to the beginning. We have chapter 12, which is 3D coordinates and vectors. Actually, no, we're not going to do, let's not do chapter 12 actually. Let's go a little further. That stuff usually isn't that awful, and I don't imagine them like being super heavy on the vectors in 3D. We may come back to that. Let's actually instead, let's review our integration techniques. So remember we have a few things that we have a few new strategies that we learned this semester. Of course, we have the ones that we have always used, such as things like power rule and U sub. We've pretty much been using since, end of 2413. Those aren't really that bad to use. Power rule is pretty straightforward. That one's pretty straightforward. You're just going to take, integral of x to the n dx will just be x to the n plus 1 over n plus 1 plus c. And then u sub, that one's pretty simple. It's essentially reverse chain. That one, remember that one we have, it's kind of like chain rule, but it isn't. Remember with that one, what we do is that's usually whenever we have some sort of composite function. So let's say we have something like 2x. We have like 2x square root of x squared plus 3. That one's easy. That one's, of course, is easy to spot because you usually have a function. You can usually identify some function and its derivative. So where you can say, like, or you can have a u du. So you can, in this example, we have an easy u to spot, which would be u is x squared plus 3, and du is 2x. And we can just double check that with our integral, which we do have that. This one's pretty straightforward to go, where we can just go ahead and do our integral of u, which is going to be 2/3 u to the 3/2 plus c, 2/3 times x squared plus 3 to the 3/2 plus c. Pretty straightforward. You may have to do a little bit of algebraic manipulation for some of this, but really the main thing you'd have to usually manipulate on this would be like the coefficient. So for example, they may get, like in a test, they may give you something to where instead of a 2, this was an 8. So then you'd have to manipulate that to go ahead and get you to the proper format. So for example, you could say 4, like you'd have to multiply times 4, for example, to get you to that 8. But once again, that one, it's pretty straightforward. So for our new ones that we learned this year, we have integration by parts. Actually, let me scroll up. We have integration by parts. And remember that one, the main one to use is if we have two functions multiplied together. That's usually the pretty easy sign for integration by parts. You may get one to where you have like one function and you can do that function times like 1 and say it's like times like 1 dx, but usually you'll have two functions. So usually what you can do is you can go ahead for this one and you have your format will be the integral of u dv. And if you integrate that, that will be u times v minus the integral of v du. So there actually is usually a priority to how you go ahead and figure out your u. And I know there's another one that some students said that they learned. The one that I learned for the priority was called Liotte. Which is going to be log inverse trig algebra, regular trig, and exponential. essentially the main idea is you want to get something that's going to be really easy to cancel out whenever you start actually having to rearrange things. And this one, you may have to do it a couple times. And the other thing that you could run into is this one, to where you could end up to where you circle back around to the same point. So like, for example, like the classic example of this is like your secant integral. To where you kind of ended up, it's like your integral secant of x is in something 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 plus secant of, or like minus secant of x, and then you kind of have to, you know, move that back around. You could run into that. I doubt you will, but that's just a thing to keep in mind with integration by parts. Next thing we can talk about is trig integrals. So you have a few important formulas to remember. So make sure you you go over your Pythagorean identities. Make sure you check your power reduction formulas. And there's also some miscellaneous trig ones like double and half angle. I know there's a handout on e-learning. Check that to see which ones you need to know. If they give you some, because some of those will expect you to memorize. Other ones, they may just give it to you if it applies to that problem. But the big ones that you really, really, really need to know, Pythagorean and power reduction, those will just follow you. The other things you also need to pay attention to are those new integral formulas that we memorized, such as integrals of secant, tangent, and they could potentially give you cosecant, cotangent. They could throw that out there, but you're more likely to see secant and tangent on there. So your main things that you can pay attention to with your trig integrals is look at the grouping. So usually what you'll have is you'll usually have sine and cosine together, tangent and secant, or cotangent and cosecant. And usually with all of these are all going, usually what you're going to do with these is you're going to do some sort of U sub. You're usually almost always going to use some sort of U sub with these. So usually, like, you may have sine and cosine, you'll usually set sine for your U, cosine for your DU, or something along those lines. You may have a couple. Sine and cosine could get interesting though. You may have to use power. You may have to use power reduction on some of those though. Next strategy we have is going to be trig sub. So that way you definitely need to make sure you know your Pythagorean identities. Like, that's essentially the whole basis of trig sub. So just make sure you know those. And just make sure you know some like basic, and once again, make sure you know your basic trig formulas and identities. Slash and their integrals. They may throw something to where you have like integral of tangent at the very end. That's usually a good one to kind of memorize. So remember, this one is usually, you'll usually have a form, there's going to be specific formats for this one, remember? So you're going to have either a squared minus x squared, a squared plus x squared, or x squared minus a squared. And remember, these all have a specific identity that they correspond to. So for that one, x is a sine of theta, x is a tangent of theta, and x is a secant of theta. And these are kind of, once again, just a modified u sub. And essentially the review section for chapter 7, they pretty much said all of your integrals are usually going to come down to integration by parts or u sub. So that's just a thing to keep in mind. And the other thing you have to remember is just remember to convert back to x. And just double check your triangle. You should usually end up back where you start. You kind of usually circle back around to where you started whenever you build your triangle. Last one, yeah, let me think. I think last main strategy is partial fractions. So this one is going to be, you're going to see this with rational functions. So essentially the format will be like f of x is equal to p of x over q of x. And the big thing to remember for this one is if the degree of p is greater than or equal to the degree of q, you have to long divide. Otherwise, it's going to mess up your partial fraction. And just to remember the basic rules for that one is so usually you're going to, you have a format associated with what your factors look like in your denominator. So if you have ax plus b, just plain ax plus b in your denominator, when you actually get your like partial fraction decomposition, that will turn into like an a over ax plus b. So just a constant over that linear. If you have a linear raised to a power, then you're going to go ahead and repeat that as long as you need to. So you're going to do a over ax plus b to the n plus b over ax plus b to the n minus 1. And you're going to keep going and adding those until you get just subtracting 1 each time until you get back down to ax plus b. And then lastly, they could give you a quadratic, like an unfactorable quadratic, and that would look like ax plus b over ax squared plus bx plus c. If for some reason you have something higher than the power of 2 when you're as one of your factors, just know that like that the numerator will have to be like one less, like the power will be one less. And once again, same rules apply if like this quadratic is raised to a power, then you have to kind of keep repeating that, and you subtract 1 each time until you get back down to like the power, and until you get back down sort of like with this. And also, yes, and last thing, just also remember this was introduced, I believe, in this section, in the partial fraction section. Double check your integrals for your inverse trig, because those, you'll run into those as well. And similar to what we said earlier with series integration, it's based on the strategy you use is based on structure. Let's see, improper integrals. These are fairly straightforward. You can have type 1 or type 2. Type 1 is what I usually like to refer to as infinite bounds. And usually by that, so usually it'll be one of your bounds, one or both of your bounds will go to infinity. So for example, you could have some constant a to infinity of f of x dx. If you need to solve that, remember you take your limit as t goes to infinity of your integral from a to t of f of x dx. So any place where you can't evaluate that, you're going to go ahead and replace that with a limit. And then you have type 2, which I usually just think of as the discontinuity ones. So for example, let's say you have this one. Okay, this one's like a little more complicated, so I'll go ahead and put this one in there. Let's say you have a discontinuity in like the middle of your interval. Remember, you can break that up and you'll use limits as well. So you could do so for example, if you have a discontinuity c in between a and b, you can say your limit as n approaches c of a to c f of x dx plus limit as, oh yeah, c from the negative, and then like the limit as t approaches c from the positive of c to b f of x dx. Once again, similar to series, convergent limit exists, divergent limit does not exist. And all limits, if you split it up, remember, once again, like with series, everything must converge for the full thing to converge. So all the parts have to converge. And then once again, you also have a direct comparison test with improper integrals as well. So once again, it's pretty much the same thing. If we have f is greater than g, which is greater than 0, if the integral of f is convergent, then the integral of g is convergent. Pretty simple. Let's think. Applications for you to remember. Remember, we have, yeah, so applications, We have arc length. And just remember that formula is integral a to b square root of 1 plus f prime of x squared dx. All right, give me, where is exam 2? Yeah, give me just a second. Let me find, where are my notes? Okay, applications. Let me come back. I'll come back to that if I can find it. Let's think some other things that you'll need to know. Differential equations. So I wasn't able to get a ton of review in. We do have the other exam reviews for you to look at as well if you kind of want a little bit more, like, if you want to go more in depth on some of this, since I know we're about to run out of time. Make sure you know different models, namely, especially your logistic model. They could ask you a bunch of questions. There's a bunch of different questions they could ask you about logistics. I doubt they'll do anything on slope fields. And just the other thing to make sure is just practice your separable equation. So remember, all of your y's on one side, all of your x's on one side. Pretty straightforward. Chapter 10. We have parametric. So we have parametrics. So make sure you remember. I doubt they'll ask you how to graph just because it's online. So this one was pretty formula heavy, so make sure you remember your derivative of a parametric is dy dt over dx dt. It is 7. I'll probably still stay a few more minutes, but if y'all want to go ahead and leave, I understand, but I kind of I'll try to get as much done like speed round. Parametric, remember, second derivative is going to be d over dt of dy over dx. So yeah, you're going to take the derivative with respect to t of your first derivative and then divide by dx dt. Area. So area under a parametric is going to be equal to, you're going to have your bounds from alpha to beta of g of t times f prime of t dt. And remember, this is whenever x equals f of t, y equals g of t. Arc length. That is going, this one is actually low-key maybe even simpler in parametric. You go from alpha to beta, square root, dx squared plus dy squared, all under a square root. And then lastly, there is surface area of a revolution. I doubt they'll ask you this, but in case, just in case, the formula is alpha to beta 2 pi y square root dx over dt squared plus dy over dt squared dt, and this is rotating about the x-axis. And some potential questions that they could ask for this could be maybe tangent line. So of course, practice your derivatives, concavity, similar thing, or they may just ask for just plain arc length or area. Polar, okay. So a big thing, so some key things to go ahead and look over are converting between polar and Cartesian, and remember our main formulas for those are going to be x is r cosine of theta, y is r sine of theta, x squared plus y squared is r squared, and tangent of theta is equal to y over x. And then now we have to deal with calculus with polar. So remember our first derivative, that is going to be equal to dy over d theta. If worst comes to worst, you can use these and treat that as kind of like a parametric. But that is going to be, that's going to be equal to dr d theta sine of theta plus r cosine of theta over dr d theta cosine of theta minus r sine of theta. Another big thing that you could not almost guaranteed to ask you is area with polar. So remember that formula is going to be area is equal to a to b of 1/2 r squared theta. And just some key things to check is check for points of intersection, and where r is equal to 0. For like either one of your equations, check and see if there's a spot to where your radius is 0 and it goes back to the pole. Because like the biggest thing that will help you with area is symmetry. I don't know if I spelled that right, but it's final season. I don't spell well right now. All right, and then they could also, oh yeah, just another quick thing. They could maybe ask you about arc length. I think they'd care more about area, to be honest, but just in case, your formula for that is integral from a to b, square root of r squared plus dr d theta squared d theta. And I think that's everything. I can double check. I can double check the syllabus real quick and see if there's a section that I missed. But I am pretty sure that is everything. Let me look real quick. And yep, that's everything. All right, so sorry ran a little bit long. Good luck on your final tomorrow. Yeah, and just remember, if there is like any of that previous content that you wanted to review, remember we always have old weekly review videos and old exam review videos for you to look over as well. All right, so have a great weekend, y'all. Have a great summer. Thanks for being here.